Hi, this is Mary James with Passive House Accelerator. Thank you for tuning in to this special bonus episode of the Passive House podcast, recorded live at the Passive House Canada Conference in Victoria, BC. And I'm sitting here speaking with David Claus from UNBC, who gave a very interesting talk earlier today. Can you please introduce yourself and tell us what you do at UNBC?
I'm David Claus. I'm the Director of Facilities Management and Capital Planning for the University of Northern British Columbia. I'm based out of Prince George, BC, and I've been there about 14 years. What do? I look after buildings, but I also help plan new buildings. I'm a mechanical engineer by background, but then I am involved in a couple of Passive House certified builds, and I get involved on the design side as well.
And you actually had a really interesting story about a building that I wrote about a while ago, which was the Wood Innovation Research Lab, which was one of the first, if I'm correct, Passive House commercial buildings, if you would call it, or institutional buildings.
University Passive House building in Canada, for sure.
Right.
I don't know if it was the first, but it was definitely up there. It was first for us anyway. Yeah, we finished that building in 2018. And then what the talk was about was in 2023, in August, the building that was adjacent to that laboratory, wasn't our building, experienced an explosion. And then that ended up catching our building on fire. And so the talk was about how we dealt with that, how we put it back together.
And how the building fared.
Yes. Yeah. And we talk about high performance buildings and how they're comfortable to live in and they use less energy and do all this amazing stuff for the planet. But one of the other byproducts is, and that's what I was talking about, is that they're actually more resilient in the face of disasters. Now, hopefully all of our buildings don't experience what this building went through. But the way that the high performance building reacted to that made it easier for us to put everything back together and get it operational again.
And as a little bit of background, it was essentially one wall that really faced the brunt of the fire, although there was some other water damage that occurred as a result of the fire. Can you talk about what happened to that? Well, first tell us what the basic wall assembly was that was facing the brunt of the fire.
So the building is basically a square, viewed in plan. It's 1 story tall in that it only has mostly a ground floor. There's a mezzanine on one side, but it's 3 stories tall in overall height because of the kind of structural research that we do inside the building.
And it's mass timber.
It's a mass timber building as well. Yes, it has large glulam posts and columns that hold it all up, big timber frame. And so what happened was when the building next door exploded, there's a shock wave that came through and it caused the whole building to shake. In fact, it flexed over and then sprung back. And that's really a function of the mass timber construction. It makes a flexible building. If that had been a concrete building or a cinder block building, it would have cracked and not come back. And so it flexed. And then there was parts of the building next door actually impacted our building. There was some projectiles that came and damaged the exterior cladding, and that allowed, where the damage occurred, that allowed the fire to actually get through. So the building continued to burn next door, and then that caught our building on fire. And the building assembly is, like I said, mass timber frame for the structure. So you've got big posts and beams on the inside of the building. And then as you work your way out, we've got an OSB sheathing layer, and then about a 22-inch deep open frame wood truss. And then in between those trusses is filled with mineral fiber insulation. And then on the outside of the trusses is another layer of OSB and then Tyvek rain screen and metal cladding. So the metal cladding protected us from the fire, but eventually that cladding gets hot and that caught the Tyvek behind it on fire. So now we have fire burning in our rain screen cavity. And then eventually that was able to burn through the OSB and start trying to light the trusses on fire. But trusses that are encased in mineral fiber insulation don't really burn that well, which is good for us. Meanwhile, as this is all happening, the firefighters are trying to put the fire out by spraying water on the outside, but that metal cladding did a really good job of keeping the water out, which meant that the fire could keep burning for some time. Eventually, though, the cladding came off. The fasteners that held it in, the wood that they're embedded into, burned out too much. And the fire department also figured out that they could use their water as a jet to blast the cladding off, which was helpful because then the water could get in and actually start putting the fire out. Eventually they got the fire put out, but where it had been impacted by some of the debris, it burned right through the wall in an area, I don't know, size of, say, a dinner tray. And in that spot, when the fire burned through, we got flames inside the building, and then the sprinkler system, the fire suppression system inside the building did its job. The one sprinkler opened up, dumped a whole bunch of water on that part of the fire, put it out pretty much immediately, which was good. We don't have a lot of fire damage inside the building. But nobody turns that sprinkler off. And so then that sprinkler kept it going for hours and hours and dumped several inches of water throughout the whole building, which meant that the building kind of had to deal with both the impact of the explosion, which in some ways functions kind of like an earthquake. Then it dealt with the fire from the outside. And then it also had to deal with the flood from the sprinkler system, putting water throughout the whole thing. So lots of disasters all at once. And then we spent about the next 10 months or so putting the building back.
But there is a happy ending to the story.
There is, yes. We did get it back together. And initially, what we did is we decided we were going to bring back the original team. The building at that point was only about 5 years old. And so we got the original architectural team. We brought back the contractor that had originally built it, a lot of the same suppliers, some of the same tradespeople even. And we said, look, we got to build it exactly the way we built it the first time. And initially there was some nervousness about a passive house and a high performance building. And how do we put it back? Can you even fix it? Well, of course we can fix it. And we were able to show that, look, we just take it apart piece by piece and put it back together the way we built it the first time. So we did all that. And the building's thankfully up and running now.
Sorry, I just to interrupt you, because the great news also was it was a panelized construction. So in some ways that simplified the rebuilding process.
Yes. So that the wood timber frame structure holds up. It's called the gravity resisting frame. And then these panels were screwed onto the outside of it and then insulated. And you're absolutely right. They were prefabricated off site. And so after the damage, we were able to take off 8 panels that had been damaged and replace them with 8 new panels. And it made the reconstruction fairly straightforward. We joined up all the air barriers and things like that again, added the insulation, new insulation back in, and then the building's back to its original performance, or very close to it.
It's really such a great story as far as the resiliency and the air tightness, I'm sure, helped reduce the fire spread. And you also had some interesting comments on the mineral wool insulation and the advantages that you saw from using that.
Yeah, absolutely. So the mineral fiber insulation, we could have blown cellulose in. That's the other thing you might do in a deep cavity like this. During construction, they made the original choice to use mineral fiber, and it turned out very well for us. So the mineral fiber doesn't burn. No matter how hot the fire got, it's not going to degrade. So it continued to insulate the building. We didn't even melt the interior air and vapor barrier that was on the inside of that insulation, except for where the fire burned right through, but everywhere else it was fine. So the mineral fiber kept the building from having too much damage from the heat, but firefighting efforts put tons of water into that wall assembly in a couple of different locations. And one wall in particular that wasn't damaged, but the fire department thought that the fire may have gotten that far. So they put a hose into a hole at the top of that wall and dumped water into there for hours. Well, months later, when our building envelope specialist is there and he's checking over the building, he was quite concerned that we would have water damage and particularly mold and structural damage to the wooden members inside that wall because of all the water that was dumped into it. And when he opened it up, we didn't find any of that. What we found, in fact, was the wood inside that wall was drier than some of the wood inside the building. And the reason for that is that the mineral fiber, which was the insulation in that wall, it drains water really, really well. It won't absorb any itself. And then the wall assembly, as it was designed, it has a breathable membrane on the inside and a breathable membrane on the outside. And that whole wall is designed to dry itself out under normal operating conditions. And it did that. It did that, exactly. It worked. Like we sometimes talk about these high performance buildings, and yes, they're good for comfort and things, but if we build them right, they look after themselves.
And I appreciated the comment you made at the end about that this building was a certified passive house building, and how certification process provides a check to make sure we are building it right.
Absolutely. As far as I can, all the buildings that I'm involved in, I'm pushing for certification. It's a check on the overall design that all the components work together the way they're supposed to. If you get a good certifier, it's not a lot of money, but it's money well spent.
And finally, you also mentioned at your own home, you're doing an interfit.
You bet. Yeah.
I look forward to hearing more about that.
Yeah, I'd be happy to share about that. We at home, the stories of the shoemaker whose kids go barefoot come to mind, and I'm like, we know how to build buildings better. I know how to build buildings better. So what can I do about our house at home to bring it into the 21st century and hopefully beyond?
Well, maybe in a future podcast episode, we'll get to hear about that. And thank you so much for your time and for stopping by. I really appreciate that.